All right, let's go over a couple of the more important things that we should have covered today that I was hoping that we'd be able to get to in our discussion problem set. I think I got a little overexcited about this because this is a really important point in organic chemistry. When you are trying to react something, you might want to remove a proton from whatever species you have here. And I was thinking of the videos that they used to have years and years ago. They used to have that will it blend video. So this is kind of like that. Will it deprotonate? That's the key point that we want to know. What base do we need if we want to remove a proton from an alcohol, let's say? So let's take a look at this one. So when you react an alcohol with a base, you want this side to predominate. So you don't want one of those equilibrium where it goes back and forth and it might be the starting material and you might be the product. You want to have this be the favored side because you're trying to make this product, and so you want it to go to the right. And in addition to this deprotonated alcohol, you will also get the conjugate acid. So you're going to get this deprotonated alcohol, this is what you want, and you're going to get this conjugate acid. So on this side we have this as the acid, and on this side we have this as the base. And if you remember, the favored side is the one where we have the weaker acid and base. So we want this to be the stronger acid and the stronger base, and this side to be the weaker base and the weaker acid. And that means that this conjugate acid is going to have a larger pKa because we want it to be a weaker acid, and the acid that we are trying to deprotonate has to have a smaller pKa. So when you're trying to pick a base that's going to deprotonate what you want to deprotonate, you need to pick a base whose conjugate acid has a larger pKa than the thing you're trying to react with. Okay, so if you're trying to react with an alcohol has a pKa of around 15-ish. So the pKa of an alcohol is around 15, and so you're going to want to pick a base that has a pKa hopefully a lot more than 15. So what we need to do here is write the pKa's of the conjugate acids of all these different bases to see which ones would be appropriate to do these reactions that we've listed here. So I will go ahead and write that down here. So pKa of the conjugate acid is what we're going to write in blue over here. I don't think I also have room to draw the conjugate acid, so that might be a good practice for you to do. All right, starting with this one, the conjugate acid of this thing would be a carboxylic acid. So the pKa of this would be around 3 to 5. The specific one I've drawn, acetic acid, has 4.74, but if you just know that it's around 3 to 5, that's good for this carboxylic acid. The conjugate acid of this anion is ethanol. It's an alcohol. And so alcohols in general have a pKa of around 15 to 16. So that's what that one is. Let's skip this one for now because this is not one of the ones that we're working with this chapter. I got a little bit too excited down towards the end. I think if I had left off D and left off V, it would have gone a lot better today, but I'll get back to that because it is kind of interesting. An amine itself, something with NH2 here and no charge, has a very, very high pKa of around 40. So this is not something that you're normally going to see in a biological system or in water at all, because this could not really exist very well. It would immediately grab a proton from the water or anything else that's around. So this is going to be kind of rare. The conjugate acid of an amine, though, an ammonium ion, would have a pKa of around, 9 to 11? 9 to 11. So around 10 or so. So this could exist in water. This is, could exist in water, like hydroxide can exist in water. This can exist in water. These two we're not going to see very much in water. If we worked with these compounds, they would have to be organic solvents that are not easily reactive with base. I apologize. I thought that your textbook had given the pKa's of some different types of carbon, but I was thinking of a different chapter. So your textbook doesn't really even talk about that, this chapter. So let me write it in a different color to show that this is not something that we're going to be covering yet. So propane would have a pKa of around 60. I put that in a different color to show that this is not something that we even know about yet, but we can use it anyway in this problem. So now we need the pKa's of the acids that we're trying to react. And again, this is one that we've covered, so we have 15 here that we've covered in the chapter. Our general alcohol is about 15. Our protonated amine is around 10. We've covered that in the chapter. This one is about 40. So we did mention that in the chapter, even though it's kind of impossibly difficult to deprotonate. We did mention that. This one was not mentioned in the chapter. Again, I thought that it was, but I was thinking about a different chapter that I had been working on the other week. So this is, first of all, what I'm trying to draw. Some people were confused about what I was trying to draw. I'm really trying to draw a triple bond so I can try to remove this proton over here. We did mention how this proton is more acidic than ethane, and this one would actually have a pKa, since we're talking about it, of about 25. So not that easy to remove, much easier to remove than the proton of an sp3 carbon over here. So now we have our pKa's of these acids over here. The bases that are going to work are the ones that have larger pKa's. I'm just going to erase this to get some room though. So to be able to do reaction A efficiently, we need a base whose conjugate acid has a pKa of higher than 15. We want it higher than this acid over here. So for this first reaction, we need something higher than 15. So this is not going to work. Compound T is not going to work. Compound U will maybe work a little bit. It'd be like a toss-up. You'd get a mixture of like half reactant and half product, so that's not the best. Compound V, if we had some of it, it's kind of dangerous to work with, but that definitely would deprotonate this alcohol very efficiently. Also, compound W would work, and compound X would not work because we don't have a larger than 15 pKa. So for this one over here, we would need a pKa of greater than 10. So compound U would work for this one because we have a pKa of 15 for compound U. V would also work, and W would also work. X would be kind of a toss-up. You'd get half and half mix, so that would not be a very efficient choice for that particular reaction. So I'm not going to put it in the list here. So this one we need a pKa greater than 40, which is probably why I listed compound V as one of our possibilities, even though it's not supposed to be here yet. But it would work for this reaction, definitely, for sure. And for these ones over here, we'd need a pKa of greater than 25, which again would be V and W. So V and W are our strongest bases. They're so strong that you can't even work with them in water because they will just react with the water quite violently. So we are not going to be working with those in lab at all this year. All right, since I'm talking about some acids and bases, I think we're actually closer to where I wanted to be than it felt like this afternoon. So one of the big things is that I wanted to emphasize how compounds look at different pH. And so I wanted to get to this chart in your note packet 2.10.1. What page is this on? Page 23. So let me just go over this as well, since I'm making a video. For these substances, I put the specific pKa. So instead of just saying that a Ammonium ion has a pKa of around 10, like between 9 and 11. I just put a value for the pKa. Let me just go ahead and point this out. When you put a benzene ring on there, it changes the chemistry of the group. So just for now, know that an alcohol with a benzene ring is not going to act like a normal alcohol. An ammonium ion with a benzene ring is not going to act exactly like an ammonium ion. So I just got a little bit of a variety here because I wanted things with different pKa's. So the important thing is that we have the pKa given to us, and so we know about what pH we have the 50-50 mix. So here, this example over here, this ammonium ion with pKa of 11. 11 is the pH at which you have this acid form as a 50-50 mix with the basic form, which would be a proton removed from this acid would give you the base form. So we have a 50-50 mix of these two compounds. If we go to higher pHs where there's less H+ ion around, this amine is not going to be able to get any protons, any H+ ions. So there's not a lot of hydrogen ions around at this pH, so the amine does not get one. We just have the basic form. If you go to lower pHs are where there's lots of hydrogen ions around, and so the amine can have one. So if if there's a lot of supply, then you can grab what you need. So that's what's happening here at these lower pHs. And the pH that's equal to the pKa, that's where it makes the switch. This particular compound has a pKa of 4.8. So this is at pH 4.8. That's the point where we have a 50-50 mix of this acid form and the base form, the deprotonated form. And the base form of the carboxylic acid is missing this proton. This is the proton that goes away to get the conjugate base over here. So we have a 50-50 mix. At lower pHs, there's lots of hydrogen ion around. So this carboxylic acid can keep its hydrogen, it can keep its proton. At higher pHs than 4.8, there's not enough around for this carboxylic acid to be able to keep the proton. So it's going to exist in its deprotonated state, or its conjugate base form at all these high pHs. All right, so 9.9, we don't have 9.9 listed, so we don't have a box where it's going to make the switch. It's going to make the switch at a pH of 9.9, so kind of like at this point over here. So higher than this, if it's around more basic solutions, then we're going to have the basic form of the alcohol. We're going to have the deprotonated form at these higher pHs. And at pHs lower than 9.9, which would include pH 7, we're going to have the acid form, the protonated form. So it's going to keep its proton because at these low pHs, there's plenty of proton to go around. Okay, so 4.6. We don't have a 4.6 here. We have a 4.8, which is pretty close. So I'm not going to say that it's a 50-50 mix, but I'll just go ahead and use this box because it's pretty close to 4.8. I'll just say that it's a mix because we would have both around at this pH, a substantial amount of both. And by both, I mean the acid form that has the 4 bonds to nitrogen with the positive charge, and the conjugate base, which would just have nitrogen with 3 bonds and a lone pair. So these are the two forms that are present, the acidic or protonated form, the basic or deprotonated form. And at higher pHs, there's not a lot of proton around, so we're going to have this basic deprotonated form. There's not enough protons around, so it doesn't get one. It doesn't get to keep one because there's not a lot around. But at low pHs where there's lots of proton to go around, that's where it gets to have one attached to it. So by the time you get to this fairly low pH, 2.5, so this is a fairly acidic solution, there's lots of protons around, so all of these species are in their protonated forms. By the time you get to very high pHs, there's not a lot of proton to go around, so all of these molecules are in their conjugate base or deprotonated forms, and then they change over at different pHs. I've got this one over here. Here, here, here is where it changes, and here, just depending on how acidic the conjugate acid form of the molecule is.